Here's a poisonous example. We feed it forward through the network and get an output. Each output node has an associated cost. We add them up to get the total cost for this example. Our goal is to reduce that cost, which means finding the gradient for every weight and bias. It looks complicated, but as you'll see, it's easier than it looks. The key is that we start at the output layer. We know each node's sum and activation, so we can calculate the node's gradient, and then multiply it by each weight's input, which is just the activation from the previous layer. This gives us the gradients for all the weights and biases in the output layer. Now we'll take a step back and look at the weights in the hidden layer. What happens if I were to change a weight here? We know that changing the weight changes the sum. Changing the sum changes the activation. We know this one too. But what happens when the activation changes? The cost from every output node changes. What if there were 100? Let's just focus on this one. How can we tell what changing the activation will do to the cost of the poisonous node? We'll use the chain rule and see what happens. Changing the input changes the node's sum. Since we're only changing this one input and holding everything else constant, the sum will change in direct proportion to the weight. If the weight were 0, changing this activation wouldn't affect the output at all. So this value is the connected weight. Next, as the sum changes, the output activation changes, which changes the cost. This product we've already computed though. It's the gradient for the output node. Thanks to the chain rule, we just multiply these pieces together to find out how the cost of the poisonous node changes as the activation changes. So what about the other output nodes? Same process. Each connection gives us a similar piece, the connecting weight in the next layer, multiplied by that node's gradient. We sum them up to get our result, how the total cost changes with this activation. We have the cost gradient for this weight. Doing this again for the next weight, these are the same two values, which is the node gradient for this node. We'll store it to quickly determine the gradients for all the weights in the node. We'll do this for all the nodes in the layer. And if there were more hidden layers, then we keep going backwards through the network, layer by layer, repeating this process. Eventually, we'll hit every single weight and get its gradient. We do this for all training examples and use their average. You can see that each training step gets faster when we use backpropagation. As the number of weights grows, the difference becomes massive. Backpropagation gives you all the gradients in a single pass, where finite differences would need one pass per weight. That means it could be tens of millions of times faster.